Okay, on to our final chapter. Okay, so this is about what's called multiple integration. Now, if I was to ask you what integration is, there's a couple of things that I'd be kind of happy with as answers. One of them would be that integration is about finding areas under curves. That's a pretty good answer. What's reasonable answer for you to give me is to say that integration is the opposite or the inverse of differentiation. Personally, I would call that anti-differentiation, and integration is the thing more concerned with finding areas. But I'm going to give you a different definition of what integration is, and then I'm going to kind of explain what it is. And this is something that you should probably already be seeing in your structural engineering modules. Integration is adding up in this. Now, this is all kind of tricky and there's all kind of pitfalls here. It can all be fixed using, like, pure mathematicians worry about this. Everything I say can be made rigorous. Integration is adding up infinitely many infinitely small, and I'm going to go with just objects. Now you can get rid of the infinitely if you adding up many small objects in a certain sense, but for us integration is adding up infinitely many infinitely small objects. And the question is, how the hell does this make sense? So what we're going to do is we're going to think about the area under a curve. So this is the kind of thing that you would have seen before. So let's draw a little curve here, say something like this. Okay, and we're interested between A and B. These would be called limits. And what we're going to do is we're going to estimate this area by chopping the area up into many small areas. Okay, so roughly, so you've got this area, this area, this area. Now I'm chopping this relatively finely, but what we're going to do is chop it finer and finer and finer so that these areas are smaller and smaller and smaller, but there's infinitely many of them. I'm going to exaggerate when I go along here. I'm going to exaggerate the width because they're all supposed to be equal width. Okay, so this is an exaggerated version of one of these. To estimate the area, chop the area up into many small areas. Will be in the what's called the limit, infinitely many infinitely small areas, which we approximate using rectangles. So what we're going to do is, so this will be xi, and you can we're going to approximate the area in this little strip here. So this small area here, take the midpoint. Now I have quite missed the midpoint, but anyway, it's supposed to be the midpoint, and form a rectangle whose height is the value of the function at the midpoint. Then the height of this is f of xi, because remember the coordinates for a function, the graph of a function, are input output. The output would be f of xi. So the height of this little rectangle here is f of xi. The width is delta x. Now they're actually all delta x. So this one is just not to scale. Maybe in case anyone just walks in and just says, what the hell is going on? This one is not to scale. And we can do this for all these little areas. Okay, so we approximate their height using the value of the function. Okay, where xi is a midpoint, and their widths are all equal to delta x, which is the width of this, which is b minus a, chopped up into n, and there's n rectangles. Okay, so this is an approximation of this little area using a rectangle. So what is the area of this rectangle? Well, it's just height by width. So what we have is that the area, the small area AI. So what I mean by AI is, see the curve with the curve and the area under the curve between those 2 points. I'll call that AI. AI is approximately the area of the rectangle
And the area of the rectangle is the height, which is f of xi, times the width, which is delta x. Okay, so therefore what is the area of all the rectangles? So that will be, add up the little areas, okay, it'll be approximately the area of the first rectangle, so it'll just be the height, the value of the function at the midpoint, times the width, so it'll be like f of x1 delta x plus f of x2 by delta x, and actually on the previous page I used big N there, plus dot dot dot, plus f of xn delta x, and we can write this in sigma notation is add up, in terms of I, f of xi times delta x. So this is also the sum of I. So this is equal to the area under the curve. Add up all these strips with kind of curvy tops. So that'd be the area under as A1 plus A2 plus A3 plus A4. Add them all up to AN, that's the total area. And the question is, how do you make this approximation more accurate? Because here you can see that, like, it's possible that these kind of cancel out, but if I'm looking at this, I would say that this one overestimates the area in this bit a little bit more than this underestimates it. So how you make this more precise is you take the delta x, which is the width, to be thinner, which is the same as taking more rectangles. Now there are ways that could fail, but a pure maths theory of measure theory shows that it works. And so how you make this more accurate is you take delta x to be 0, which is the same as saying that you take the number of rectangles n to get very, very big. So to make it more accurate, there's two equivalent ways. You do the limit as the number of rectangles goes to infinity. That's your infinitely many, which is the same as taking the limit as delta x goes to 0. And this is your infinitely many small. And whenever you have a sum of this form and you take the delta x going to 0, the sum becomes infinite and you get an integral. So what you have is the definition of integration from a to b f of x dx is this. Now I could actually use either of these limits, it really doesn't matter. I'm saying, well, I think the one that's they're the same thing. Could I write both? Yeah, why not? Let's write both. Limit as n goes to infinity, that's the number of rectangles, that's infinitely many, slash the same as delta x going to 0. And they're both the same, because if there's loads of rectangles, they start to get very narrow. If they get very narrow and they add up to b minus a, there has to be loads of them. And this is what integration is. So integration is adding up infinitely many, infinitely small things, because this delta x gets very, very small. So whatever, it doesn't really matter what this number is, it's multiplied by a very, very small number. So you're adding up infinitely many, infinitely small things. And this is what integration is. And in terms of notation, delta is a capital Greek D. And the idea is that if delta x gets small, you should go from a big D to a little d. Okay? And then the idea is that this sigma is a sum. Sure, this is nothing but an S for sum. So this is what this is exactly what this means. Right. Now let's see some examples of these. So distance. How do you find the distance traveled by a car between t equals 0 and t equals big T if the velocity is variable? So something like this. Okay. So let's take big time. This is this technically should be revision, but maybe I'm kind of pushing this thing about adding up infinitely many small things a bit harder than you've seen before. But in terms of engineering, that should be the important aspect. Okay. So how do you find this? So what you do is you chop the time interval up into loads of little small time intervals. Now I'll do a few of them and then we'll exaggerate. So imagine there's loads and then we'll just exaggerate one. So let's find the distance. Actually, this is going to come in a different way. So
we'll do it down the bottom here. So the total distance, which I think I'm going to call S, is equal to, so this is going to be the first time interval, the second, the third, this would be the ith time interval. So this would be like, we have to be careful, but we're calling this thing Ti. Okay, this technically I think would be I minus 1 times delta t, and this would be I plus 1 delta t. So the width of all of these are supposed to be the same. Again, this is not the scale. That's the little time period. So you got a big time and chopping up into loads of little times. And so we want to say that the time, or the distance traveled, is the distance traveled in the first time interval plus the second time interval plus the last time interval. Yeah, I'm happy enough with that. Okay, and what is distance traveled? Well, it should be speed by time, should it not? Now, the thing is, you have a variable velocity. So what that means is, over a small time period, delta t, the velocity can vary. Okay, so this is actually going to be an approximation here. And what we're going to say is, we're going to estimate the velocity over a time interval by the velocity at the mid time. So we're going to imagine or assume that the velocity is actually constant over one of these little time periods, and that this is not y equal to f of x, this is y equal to the velocity as a function of time. So at the height of this, well, actually, forget about the height, but so you're going to do velocity at time 1, velocity times time. Now all the times are delta t, remember this is not to scale. I'm just going to write in to scale, not to scale, times delta t plus vt2 delta t. So this is, distance is approximately velocity by time, plus plus plus. Now this is add up the velocity times dt. And how do you make this more accurate? Well, if you make the delta t to be very, very small, then the velocity can change over a small time period. And yeah, so adding up loads of small distances, you get that the distance traveled is actually the integral from a to b vt dt. So this is something you may have seen in first year mechanics, I suppose, that the area under the velocity time curve is the distance traveled. Okay, one example. What am I interested in here? Adding up infinitely many, infinitely small things. That's what integration is. Work. Now we'll go a bit faster on this. So suppose you've got work done by a variable force between here and here. Okay, say between A and B. As I said, we'll go a bit faster. Now we'll chop the distance AB into loads of little pieces. Okay, and we'll say that this is the distance xi, and that the work done here is wi, and we can say that wi, the work done, is approximately force by distance. The force is what the force would be. Again, my graph is the annotation is not correct. This is y is equal to the force at distance x. So this would be f of xi times delta x. To make this approximation more accurate, you take delta x to be small, and so the work is, you're adding up infinitely many of these small f of xi delta x, and then kind of you're implicitly saying, you might even, in engineering, you might just write that this is equal to the integral if you're taking the delta x to be small. Okay, so basically what they're saying is that an infinite sum, where all the things are infinitely small, is an integral. Okay, let's look at another example. The mass of a bar, which has, suppose it has a radially symmetric density. So what that means is, if you look at a cross section, across the cross section, the
the density is the same from the middle to the edges and everywhere else. This is a very crap drawing, isn't it? Okay, so how do you find the mass of this? Well, what you do is you chop it up into loads of little little rings, little cylinders. We'll exaggerate the middle one as usual. This is very exaggerated. So we take the width to be delta x, and we take the midpoint, and we assume that the density over this is the same. Now this is not a good approximation unless delta x is small. If delta x is very, very small, the density as such hasn't got much chance to change, and so it's approximately constant over that thing. So let's say that the mass of this little piece, which we'll call mi, I don't know why I didn't pick little mi, I think little mi is nicer, is equal to, it'll be density, which I'm saying is the density at xi. It has to be times volume. I'm a little bit concerned about my units. Well, this is per unit. So if I multiply the density per unit length by the length, I get the little bit of length. Now this is an approximation. To make it accurate, and maybe I should have written this maybe up here. So if you take delta x to go to be small, so we can do that here properly. So the mass is, add up all the little masses. I mean, how do you find the mass of the rod? Chop it up into little pieces, find the mass of each, that's fine. The mass of each rod is approximately the density per unit length times the length. But what you can do is, so take, to make this more accurate, take delta x to go to 0, and then this approximation becomes better, and you get that the mass is the integral from 0 to the length of the rod. The density is a function of distance dx. So this is a little bit of mass and you're adding it up. Okay, I think we've got one more here. So this, the moment of inertia of a rod about a point. Okay, oh, it seems to be, where is it about? Is it about the center? Maybe it is about the center. So again, I'll try and draw a rod. Now, it has to be a thin rod, both of these, otherwise things are a little bit more complicated. Nice. Oh no, actually they're okay. This one is a thin rod, I think, because we get into other issues then. So it's a very thin rod. I'll exaggerate the size of it. What I mean by a thin rod is that we can treat what is actually a three-dimensional object as a one-dimensional object. I think we're going to find the moment of inertia about the midpoint, I hope. Okay, so this is going to be x equals 0. I think that's where we're finding the moment of inertia about. Over here you've got x equal to L over 2. And here you've got x is equal to minus L over 2. Let's take a little piece, chop it up a little cylinder. Again, not to scale. Not to scale, and everything above is not to scale, not to scale. Well, actually here it doesn't really matter. It is to scale because I'm only chopping up once. So, what the hell is the moment of inertia of this? Right, let's see. We know that a little bit of a moment of inertia of this, so we'll call this actually I, and this will be the point xi. Right, I want to find the moment of inertia of this little bit here. Now, as delta x gets small, this is like a little particle, and it'll be the mass of the particle times r squared. Okay, right. So the moment of inertia of this will be, now the delta m's could be written as mi. It's kind of a similar story. So we might just see this about, so like mi is the same as delta. I think actually mi is actually possibly a better notation. Okay. So I need to do mass by r squared. Now the mass is the density at this point times the width, which is delta x. That's okay. That's okay. Times r squared.
Now, r is the distance from here, which is xi squared. Okay, this isn't too bad. Whoa, xi squared, that's okay. Now, where the hell is the row going? Okay, I think what we're going to do next is we're going to take the density to be uniform. Now then, what that means is we can pick units so that the density is 1. Now there's a bit of messing around here. Yeah, maybe I won't do that, but I'm assuming uniform density. So this will be equal to, say, some constant times, which I'll call the density constant, times delta x times xi squared. That is the moment of inertia of this, and we want to add up all of them. So it'll be accurate if you take delta x to be small, in which case because the other thing we're doing is like the distances here range, but if you take delta x to be small, essentially you've kind of only got one distance and you've only got one density anyway, so that's not an issue. So I is add up all the little bits of moment of inertia. That is add up the k rho delta x. Oh yeah, this is moment of inertia, which isn't the same thing as a second moment of area volume even. So it's actually okay. I wouldn't worry too much about this k thing. And I'm assuming uniform density. And so if you've got delta x going to 0, then you've got loads of these you've got infinitely many small things. This is an integral from minus L over 2 to L over 2. K rho is the uniform density that actually could be, if I put rho of x here, this kind of keeps working, x squared dx, ruin it. So this is the sense in which integration is adding up loads of little things. You should start seeing this in your engineering modules. So that's loads of examples. Now the next question is, how do you calculate an integral? So to calculate an integral, you anti-differentiate and then you do top limit minus bottom limit. That's called the second fundamental theorem of calculus. Now the first way you do it is you just use the tables, then you do manipulation, and then you try a substitution, and then the next thing you've probably been trained to do is do integration by parts. But what I'm saying is that we're probably mostly going to get by with directly and manipulation. Now I think I'd hope that some of the examples I looked at in the first few slides there would convince you that doing integration is important for engineering. But where I'm going to kind of say for you where it's important is you've got all these different various formulas. So here I got on page 194 these different formulas for, I think, like centroids, areas. I'm not sure what Ix is. Is it a moment of inertia? You've got second moments of inertia, all these different things. And the question is, where the hell do these formulas come from? They come from integration, by breaking the problem up into adding up loads of little small things. So that's what's what.